Welcome back to part 6 in atoms, molecules, and ions. And this is a continuation of section 2.6 if you're following along with the textbook. And so we're going to learn the rules for writing the formulas and naming ionic compounds. It's super important because if you don't understand this, you're going to have a hard time with doing reactions that comes later. So, as we said before, ionic compounds are formed when we transfer electrons in small whole number ratios, okay? And so the sum of the charges of the pluses and the minuses must equal 0 so that it will be electrically neutral. That's when it's stable. So an ionic bond is typically formed between a metal and a non-metal because that's where you're going to get the plus and the minus, and you're going to always have to have the same number of pluses and minuses from your ion in order to get that neutral overall charge. So this is what I call the swap and drop technique, okay? So you make sure that the formula is going to be neutral to swap and drop the charges. So for example, if you're going to put aluminum oxide together, your aluminum has a +3, and remember we can look at the periodic table to remind us of what those are. Oxygen is going to be a -2. So you're going to take the 2 to the aluminum and the 3 to the oxygen, and that'll give you Al2O3. With calcium and phosphate, notice we're using a polyatomic this time that you can look up on your chart. It's a -3 in the case of phosphate and a +2 for calcium. So the 2 goes with the phosphate and the 3 goes with the calcium. Notice that I have to put the phosphate in parentheses if there's more than one, because if I didn't put it in parentheses, it would look like there were 42 oxygens. So I have to put that in parentheses so I know that there are 2 of the PO4s. So there are so many compounds that exist that we use these rules worldwide to name them, so that we can label the variety of substances and that we can communicate with a common nomenclature. And so this agreement among all of the scientists in all of the world is how we do this, okay? So when we name ionic compounds, if we have a cation with only one possible charge, okay, then we don't have to use Roman numerals. But if it can have multiple charges, then we're going to have to use Roman numerals in order to differentiate between which charged ion is forming it. We'll end these in IDE for the anion, the negatively charged. So when we name them, we saw earlier, if we have an example for like sodium, which is a plus because it's in group 1, and chlorine, which is a minus because it's in group 17, sorry. And then we swap and drop. That gives us NaCl, okay? And that's sodium chloride. And I don't have to do a Roman numeral because the sodium can only have a +1 and chlorine can only have a minus. Manganese, however, can have multiple charges. And so if I am given the formula, I can figure out what the charge on the manganese is if it is with something that always has the same charge. Now remember that fluorine is in the same group as chlorine, so it has a -1 charge. So I'm going to rewrite this. So it has a -1 charge. In the formula, there are 2 fluorines. So that means that I have a -1 charge times 2, which gives me an overall -2 charge. In order for this to be neutral, I'm going to have a total of a +2. I only have 1 manganese, because if it's understood, we don't write it if it's 1. So that manganese has to have a +2 charge, because +2 times 1 equals +2. So that's why I know that this is going to have to be manganese with a 2+, so it's a 2 Roman numeral fluoride. We only write these if it can have a variable charge. Manganese could have a +4 charge. So it could have been MnF4, okay? And in that case, then it would have had to have a +4 charge, okay? So it would have been manganese 4 fluoride. So that's the importance of this. That's why we have to do it like this, so that we know which one we are talking about in each particular compound. So here's your sample problem. Name the following ionic compounds. Okay, so we've got magnesium with a +2 and oxygen with a -2. So when I swap and drop that would be Mg2O2. But in ionic compounds, it needs to be the lowest number. So those are both divisible by 2. So it's actually going to be MgO. Okay? So its name is going to be magnesium oxide. Why not a 2 there? Because magnesium is representative and so is oxygen. So they do not have to have Roman numerals. All right. The AlOH3, remember we have a polyatomic, so we have to do that, right? So this is going to be AlOH3. That tells us that it's a +3. Again, aluminum only exists as a +3, so it's aluminum hydroxide. That's the name of this polyatomic. For C, this is iron. So you have 2 irons and 3 sulfurs. The sulfate is a -2, okay? But you have 3 of those. So since that's times 3, that's a total of a -6 charge. In the formula, I have 2 irons. So 2x equals 6. So the charge on that would be 3. So it is going to be iron 3 sulfate. So that's how that works. So, and that I just had this one so you can see it all pretty. Okay, so then you are going to deduce the formulas for these. I'm not going to work these for you because you can do these. Well, wait, I take that back. I am going to work it for you. Sorry. I apologize for coughing. I've got some kind of sinus stuff going on. Okay, so deduce the formulas for these. So we've got chromium 3. Remember, this tells me that that's going to be a +3. So chromium +3. Chloride can only be a -1. It's always the same because it's a representative. So I'm going to swap and drop. So I'm going to have CrCl3. Lead 2 means I've got lead 2+, and a chromate, which is CrO4 2-. So that's just going to give me, because remember, if you swap and drop and you get 2 and 2, you're going to have to reduce that in your ionic compounds. So it's going to be PbCrO4. And this last one, potassium hydrogen phosphate. All right, this is a +1. The whole hydrogen phosphate is a 2-. So this is going to have to be K2HPO4. All right, so you're going to have some practice for these, and there are some extra practice sheets for you to work on these as well. But here is your practice problem: naming the top ones and writing the formulas for the bottom ones. And I've already put out the keys for these so that you'll be able to see if you're doing them correctly or not. Oxoanions are those that have the oxygens in them. So the polyatomic anions, so they can have 1 or more oxygen atoms. So like chlorate, nitrate, sulfate, okay? Those are 8s. We'll call them like -ATEs. So those are the ATEs, all right? If they have more than one possibility, okay, they could have chlorate ion, and then they could have another name for those, chlorite ions. The chlorite means it would have 1 less oxygen. So it goes from 8 to 8. It doesn't mean it's got 3 and 2. It means it's got 1 less than the 8, the -ATE does. And then if it has 2 fewer oxygens, if that's a possibility, then it can be hypo and then the ite. Okay, hypo and then the ite. So it's easier to just kind of see me do a few of them. Might make more sense. So BrO4- is what we call the bromate ion. This is the bicarbonate ion, bicarbonate, or hydrogen carbonate. If it's just CO3, 2-, then that is the carbonate. So adding this H, you'd either name it as hydrogen carbonate or bicarbonate. And then finally, SO3, 2- is sulfite ion, because the sulfate is SO4, 2-. Finally, hydrates. Hydrates are another type of compound, and they're kind of odd. They're written like this, like a dot and then some waters. Hydrates actually carry a water molecule as part of their formula. So their overall molecular mass and stuff like that includes that water molecule. And so you use that same, the same prefixes like we saw with like di, mono, hepta, that kind of thing. So dihydrate is 2, mono would be 1, hepta is 7, and tetra is 10. And I'm going to show you when we're naming some of the molecules in the next and last section what those all stand for. And you do need to know those, that mono, di, tri, hepta 7, tetra's 4. So you will need to know what those are, 1 through 10. All right, but that rounds up the ions and ionic compounds of naming and writing formulas.